In this video, we'll be covering the concepts of analysing AC circuits in series and parallel configurations and answering some common circuit problems. Viewers should note that the circuits discussed have only one source of energy, potential or current. This video assumes that the viewer already has prior knowledge of both basic circuit analysis in DC current and complex numbers, including Ohm's law, voltage divider rule, Kirchhoff's voltage law and Kirchhoff's current law, or KVL and KCL, reactance of both inductors and capacitors, and alternating between rectangular and polar form. Firstly, a series circuit has one shared connection point between each pair of components, while a parallel circuit has two. One might think that due to the different forms of electricity, the analysis of the circuits would be completely different, while in fact the fundamental concepts are the same. This is due to DC being a special form of AC where the frequency is equal to zero. This can be shown valid in the reactance equations. In the equations, if frequency is set to zero, reactance is equal to infinity for a capacitor and zero for an inductor, which is how capacitors and inductors act in circuits when they reach a stable state, open, and closed or short. The fundamental concepts of analysing both series and parallel circuits are the exact same in AC as they are in DC. The only real difference is when analysing capacitors and inductors, as they will alter the phase angle of current compared to voltage due to the reactance times. Current leading the voltage by 90 degrees in capacitors, and voltage leading the current by 90 degrees in inductors. To give inductors and capacitors in AC circuits phase angle, the complex operator J is used. This will only affect inductors and capacitors in AC circuits due to their reactance. To give the impedance of an inductor or capacitor, we multiply J and negative J by the reactance of the inductor and capacitor respectively. Therefore, the phase angles of inductors and capacitors can be worked out to be 90 degrees and negative 90 degrees. In a series circuit, either AC or DC, the total impedance, known as the resistance in DC, is simply the sum of the elements. However, AC does involve the complex operator J. In a parallel circuit, the total impedance is the inverse sum of the elements for both AC and DC. Again, AC involves the complex operator J. An example of both of these will be shown next. This video will cover the analysis of a circuit with elements both in series and parallel, to allow the viewer to understand both configurations and both configurations working together. Tips in analysing circuits. Redraw the circuit, simplifying series and parallel elements to show the fundamental structure of the system. Simplifying multiple elements with block elements will represent the circuit more clearly. Adding and subtracting complex numbers requires rectangular form, while dividing and multiplying requires polar form. The following series parallel circuits shown and the questions are common questions asked when analysing a circuit with this configuration. Firstly, we will calculate the total impedance of the circuit in polar form, and then we will calculate the total current. To find the total impedance, the circuit can be first reduced into block elements as seen in the diagram. The inverse impedance of the parallel network equals the inverse impedance of the inductor minus the inverse impedance of the capacitor. Solving for Z1, we give a value of negative 79.06 J. The total impedance can then be worked out to be equal to the resistance plus Z1. This gives a value of 127.48 with an angle of negative 38.33 ohms. The total current can be found using V equals IR, where the total current equals the total voltage over the total impedance. This gives a value of 1.88 with an angle of 38.33 amps.